Hello, and thank you for joining today's webinar entitled, Are You Connected to the Future? A Panduit Fiber Optic Webinar. I'm Dave Dunnigan with Panduit, and I'll facilitate this webinar. First, a little housekeeping before we begin. This webinar is being recorded. It will be available soon after the webinar on demand, and all registrants will receive an email when it becomes available. You will then be able to forward this webinar to your teams and coworkers. All lines during this webinar will be muted. Following the webinar, there will be a Q&A session. Please feel free to submit your questions utilizing the chat box in the GoToWebinar app. We will answer as many questions as possible today that time allows. Today, we'll dive into the murky waters of fiber optic networking and what the future holds. Today's presenter is Tom Kavanek. He joined Panduit in 2009 and is currently the Technical Marketing Manager for Panduit. He previously served as Solutions Marketing Manager for High-Speed Data Transit Solutions. Tom has spent his entire engineering and business career in the video and communications segment. He's well-versed in video acquisition, manipulation, XDSL, optical, and RF communications. Tom holds a Bachelor of Science in Electrical Engineering from Bradley University and a Master's of Business Administration from San Diego State University. Without further ado, I'll hand it over to Tom.
Thanks, Dave. Let's jump right in. We've got a full agenda. So first thing we'll do is we'll take a look at where multimode optical modules are going. What's the technology? What's, I'll say, the roadmap? What can we expect with multimode optical modules? And once we start covering that topic, it's going to lead to uncertainty in the data center. Technology in the data center used to progress, at least from a networking standpoint, on very sort of, I'll say, defined steps, and that's all changing. We'll talk about very quickly, two product areas, what we call HD Flex and the Pan MPO. After we cover that, we're going to talk about how far can a multimode fiber reach. That's one of the questions that customers tend to ask is, okay, yeah, there's all these new technologies, but how far can I push that, the distance? And then there's a new fiber type called OM5. So I want to talk a bit about OM5. What is it? What makes it different than the other multimode fiber types? And answer the question whether you should consider deploying it or not. Ethernet's history, at least up through 10 gig, was fairly well, I'll say, defined. You could sort of count on every time the IEEE would come out with a new networking speed, it was always 10 times faster than the previous speed. And the timing of when those standards would come out, for the most part, fairly regular. At least from 100 to 1 gig and 10 gig, every 5 to 7 years or so. Everything was, and that was the way life was, just driven by the IEEE. And let's take a look at, though, when we're migrating from 10 to 40 and 100 gig. Let's start out with 10G base SR, which is 10 gig, as we know and love so well. Duplex fibers, 300 meters on OM3, 400 meters on OM4. When the IEEE went to 40 gig and 100 gig, they sort of did it, I'll just say it this way, the brute force way, which was basically, we'll take 10 gig and we'll deploy 4 lanes of 10 gig to get 40 gig. And if 4 lanes of 10 gig is good, then 10 lanes of 10 gig has to be better for 100 gig. Since it's multiple fibers, we couldn't use the duplex LC anymore and had to go to either a 12 fiber MPO for 40 gig or a 24 fiber MPO for 100 gig. And if you take a look at that slide and you look at the reach for 10 gig, for 40 gig and 100 gig, you're going to see that the reach is shorter than for 10 gig. And you might think to yourself, hey Tom, you said that 40 gig was full lanes of 10 gig, so how come the reaches aren't the same? The reason they're not is because the module manufacturers were concerned about the cost of a 40 gig module and certainly the cost of a 100 gig module. And one way to lower the cost was to open up or widen some of the specifications on the parameters for those modules. Opening up or widening the specification means that you're going to improve your manufacturing yields. But the downside of widening those specifications for some of those components means that the reach had to be reduced. When 40 gig came out, another application sort of, I'll say, just popped on the scene, not sanctioned or not standardized by the IEEE, and that's basically using 40 gig to deploy 10 gig, which sounds sort of backwards, but basically it's a breakout application. The reason one would want to do this, like a QSFP module is maybe about only 150% larger than an SFP plus module. SFP plus modules form factor for 10 gig. And I can't remember who the systems, the switch vendor was that thought of this idea, and I should, see if I was better, I probably should do some homework and find that out, but I don't know who it is. Anyway, some enterprising switch vendors said, well, wait a minute, 40 gig is 4 lanes of 10 gig. I can decouple them and run those 4 lanes independently. And the reason I want to do that is I can now increase the density of, let's say, for example, my top-of-rack switch. And I can use here what's called a Hydra cable, or some companies refer to them as octopus cables, which I don't understand octopus because there's only 4 legs, but at any rate, 4 lanes of 10 gig on the switch side. The 4 lanes of 10 gig are decoupled, run down the cable into 4 10 gig ports on servers. Breakout application is almost always a server to switch application. So really cool idea, helps out on density. 100 gig was 10 lanes of 10 gig, and I suppose you can probably still buy those modules, but that's basically been rendered obsolete by the new 100 gig standard, 100G base SR4, which is 4 lanes of 25 gig. Obviously, 10 lanes of 10 gig are deploying 20 fibers for 100 gig. Why would you do that when I can use the exact same infrastructure for 100 gig that I've deployed for 40 gig? So if I've migrated to 40 gig, and now I want to go to 100 gig, it's as easy as replacing the active equipment, the blades, and the modules to move from 40 to 100. It's the exact same fiber infrastructure. I've mentioned breakout application, and 100 gig can be broken out into 4 lanes of 25 gig. You may have heard about 25 gig in the trade press. That is a result of the standardization for 100G base SR4. And at this point, the market begins to fragment. What I mean by that is Arista, some time ago, when 100G base SR10 came out, Arista said, there's 4 fibers not being used. I can increase the density of the switch even further by lighting up those 4 unused fibers to create 120G base SR12. Now, I suppose you can connect 120 gig from one switch to another switch, but it was essentially for breakout applications for density. And so this is an example of, I don't want to say Arista going it alone, but providing some product differentiation, and which started to fragment the market. Cisco further fragmented the market by deploying developing and deploying what's called BiDi, short for bidirectional. It's 40 gig Ethernet, but only uses 2 fibers. And the beauty with BiDi and the motivation for Cisco was it allowed customers to move to 40 gig, but remain on an existing 10 gig infrastructure. How does this work? Basically, it uses 2 wavelengths, 850 nanometers and 900 nanometers. And they're not shot in the same direction, they're actually shot in opposite directions. So if we look at the diagram, on the left-hand side, there's a VCSEL, the laser, shoots out a beam at 850 nanometers and goes through what I like to refer to as a 2-way mirror. And, every time I sort of call it a 2-way mirror, my friends at the corporate R&D lab sort of cringe and roll their eyes. But trust me, it acts as a 2-way mirror. Goes through the 2-way mirror, down the length of fiber to the module at the opposite end, where it bounces off the back side of that mirror, and it's reflected into a detector. At the same time, starting on the right-hand side, a VCSEL running at 900 nanometers, laser shot through the 2-way mirror, runs back up the length of the fiber, hits the 2-way mirror, and is reflected to a detector. If you do that twice, 2 lanes, 20 gig, have 40 gig, And the reach is 100 meters for OM3 and 150 meters for OM4. Now, this was important, and we worked with Cisco quite a bit on developing BiDi and characterizing optical fibers for them. That reach is important because Cisco's goal was to have BiDi replace 40G base SR4. And that's why the reach had to be the same. That's why the form factor is QSFP, so it plugs into a 40 gig slot. Even though it uses duplex fibers, one could have said, well, why not use SFP? Because that's what was used for 10 gig, but then you wouldn't be backward compatible. And Cisco really wanted to deploy BiDi and replace 40 gig SR4. So if we take a look at what's available or soon to be available on duplex fibers through 100 gig, we have 10 gig, 25 G base SR. There's Cisco's 40 gig BiDi. 50 G base SRs being developed or standardized at the IEEE. And then same with the 100 G base SR, or sort of going out on a limb, but I can sort of conjecture that Cisco might want to deploy a 100 G BiDi. So let's take a look at some of the technologies that are on the horizon for multimode fiber. What are some of the ways that the optical module manufacturers, what are they looking at to crank the speeds even faster beyond 100 gig? The first one is faster VCSELs. So instead of the VCSEL running at 25 gig, it's running at 50 gig. Now, sort of need to, I don't want to say correct myself, but the VCSEL itself for 50 gig isn't running at 50 gig. The VCSEL can't be clocked faster than, I don't know the exact number, but somewhere between 25 to 50, you just can't crank it any faster. So for 50 gig, what the VCSEL suppliers do is they're just going to leave the laser on continuously, and they basically put a shutter in front of the VCSEL and operate the shutter at 50 gig. Another way to speed things up is to use a more advanced modulation technique. So what we have here is what's called an eye diagram, and this is what an eye diagram that, let's say, for example, would represent 10 gig or even 40 gig for that matter, 4 lanes of 10 gig. And basically, it's on-off keying. The laser's not on for a 0, and it's turned on for a 1. And by turning it on and off at 10 gig, you can run 10 gig down the fiber. But let's add 2 more layers. So now I can send 2 bits per symbol down the fiber. And the way this sort of works is, I said it was on and off for on-off keying. Here for PAM4, the laser is off. And when it's off, it represents a 0 and a 0. If it's sort of off, it's a 0 and a 1. If it's sort of on, it's a 1 and a 0. And if it's all the way on, it now represents a 1 and a 1. So now I can send 2 bits per symbol instead of the 1 I was sending before. The downside of PAM4, if there is one, would be you might take a look at that diagram and realize PAM4 might have a problem operating. PAM4 might have a problem operating, let's say, if in a noisy environment, or if the receiver starts to age and performance and noise gets in the system, because it'll be harder to detect the 1001 because the spacing between them is now narrower than it was before. Time for a poll question. What is the highest speed link that's been deployed in your data center? 1 gig, 10 gig, 40 gig Ethernet, or 100 gig? The reason I'm sort of curious is because one of the blog postings that I made some time ago, and we always talk about speeds and faster speeds, which is what we're doing here in this webinar. But one of my most popular blog posts had to do with cleaning the end of the fiber, something very mundane. And I'm wondering if we're talking about high speeds, but has the end user community not adopt these faster speeds as we think we have? So it looks like the majority of you have already deployed 10 gig, and I'd say a quarter of also deploying 40 gig. So I'd say good news, but okay. So yeah, we're talking about these faster speeds, and it is important. Thanks for filling out the poll. Last technology for increasing speeds is wave division multiplexing. And basically, instead of 4 physical lanes, we now have 4 wavelengths down one length of fiber. Wave division multiplexing is now just starting to be adopted in data centers, but it's been deployed in the cable TV plant for, I'm going to say decades, but trust me, a long time. And it's only now that the cost has come down enough where it could be deployed in the data center. All of these technologies could be combined. They're not mutually exclusive. So I can do a PAM4 on multiple wavelengths, or I can have a 50 gig VCSEL and still use PAM4. And since they can be combined, here Panduit some time ago said, okay, if you combine these things together, how fast can you go on multimode fiber? So let's start with 10 gig. My little color code down below is it's yellow. It's an IEEE standard, either existing or will soon exist. Green, optical module manufacturers have sort of done their own thing and came out with modules. Blue is Tom Kavanik's prediction of the future, which is always a dangerous thing. And if there's a thick ring around it, that means it's available. You can buy it today, off the shelf, ready for immediate delivery, as they say, or it has been demonstrated. Meaning you may not be able to buy it, but it has been shown as a viable technology. So there's 10 gig. 40 gig, we have Cisco's BiDi. That's been out now for, I'm going to say about 3 years, I think. And then we have 40G base SWDM4. That's 4 wavelengths running on duplex fiber. This is a technology that's been demonstrated, and I believe is now available from Finisar. 50 gig is being debated at the IEEE. Well, maybe as we speak, or maybe it was last week. But at any rate, the IEEE is standardizing 50 gig. For 100 gig, Tom's predicting that Cisco will have 100 gig BiDi. And down below is 100G base SWDM4, which Finisar demonstrated at the last OFC conference a couple of months ago. And in fact, Panduit and Finisar partnered to put that demonstration together. So the SWDM4 module 100 gig was running using Panduit fiber. You can get to 200 gig several ways. For BiDi, apply 50 gig VCSELs using PAM4, 2 wavelengths. We can also get to 200 gig by taking that 50 gig technology and adding multiple wavelengths to that. Or we can get to 200 gig a third way, which is 4 wavelengths and 50 gig VCSELs. But we can go even further if we combine all the technologies together. We can 4 wavelengths, 50 gig modulation, and PAM4. 50 gig VCSELs and PAM4 modulation gets us to 400 gig on duplex fibers. Another poll question: how strong is your desire to remain on duplex fiber? Since some of these technologies have popped on the scene, several customers have expressed interest that they want to stay on duplex fibers, and how can they do that? So is it a requirement, meaning you're going to do it? You have a strong desire, you'd like to, but it's not a requirement, or quite frankly, you don't care. So it's basically either running to don't care, or you'd like to, but not a requirement. So, okay, sense is sort of cool, that'd be really great, but if there's another technology that could be, we could adopt sooner than we need, then we'll go ahead and we don't care. Duplex multimode fiber roadmap. Is what I just shown a certainty? Well, no, it's not, because, looking into a crystal ball, always a little cloudy. But it does show that the optical module market is segmenting and fracturing. And what I mean by that is, one of the very first slides, I had shown that the IEEE sort of rolled out new standards pretty much on a fairly consistent time schedule, and was always a factor of 10 faster. And the issue for the optical module manufacturers was that they could develop the module faster than the standard was put together. So let's say it took like 5 years to create a standard. They could probably develop the technology for the module quicker than 5 years. And in fact, if you're developing a standard, you want to do that. You want to, when you create a standard, make sure that the technology that is supporting that standard is available. Otherwise, you just created a standard that can't be implemented. The problem with that for the module manufacturers, though, was since their module were ready, they're already sort of implementing the standard before it was ratified. The module manufacturers started beating each other up in order to get business, so that when the market actually started to take off, all of the margin was wrung out of the market. Basically, not a whole lot of profit left. Well, one of the ways to combat that is, and just generally speaking, if you come out with a differentiated product that provides extra value to your customer, then you can charge more. And that's one of the reasons why modules outside of the influence or outside of the sphere of the IEEE are emerging on the market. The other issue here is the number of fibers. So I've described two, duplex fibers, 8 fibers. There's even talk of, let's say, 32 fibers. There's 4 fiber work being done at the IEEE. So, whether it's 2, 4, 8, 12, who really knows? So what to do? The first thing is you need to stay as flexible as possible. Basically, don't paint yourself into a corner. And so you want to avoid options that are rigid. And an example of that would be a base 8 system. A base 8 system uses trunks and interconnects that are multiples of 8 fibers. And it only supports configurations for duplex fibers and 8 fibers. That's it. So if you want to deploy, let's say, a 4-fiber solution, you would have a problem with base 8. If you want to deploy 12 fiber, you have a problem with base 8. And 40 gig SR4 uses 8 fibers, and you might think, okay, that's fine. I only need 8 fibers. 4 fibers in the middle are unlit. But what if some enterprising systems company decides, you know what, I'm going to light those 4 fibers up and provide 60 gig using a 12 fiber MPO? You wouldn't be able to take advantage of that technology if you went with a base 8. It's also not efficient. There's more trunks to manage. There's more cassettes to install and maintain, and I'll show a picture of that in the next slide. And day one, meaning day you deploy, and let's say you're deploying duplex fibers, the day you deploy, you're going to have to write a check that's 20% larger. And if it just so happens you never migrated duplex fibers, you now just spent money that 20% more that you didn't have to. So we'll take a look at what I meant by costs more, more to manage. On the left-hand side are 3 base 8 cassettes, and on the right is a 12 fiber cassette. So you can see you've got more cassettes you have to install. The cost of those 3 cassettes is more than the cost of that 1 cassette on the right-hand side. You've got more trunks to manage. You can see that there's 3 8-fiber MPOs. So there's, and on the right-hand side, there's only 1 24-fiber trunk that's plugged right directly into the cassette. So it's less cost, easier to install, less time to install. It's easier to manage. Another part of the flexibility is our HD Flex cabling system. High density. And the reason that it's flexible is that it can support 12 fiber, 24 fiber cassettes and 12 fiber cassettes. So you can start out one day using 6-port cassettes, and in the future, if you wanted to migrate to the larger cassettes, you can do that. And you can do that just by removing one of the middle rails. You can see either in the panel, in the enclosure, there's a 6-port cassette, and then for tight space or where you may not have a whole lot of room, we have a 0RU bracket. Also, from a flexibility standpoint, is the PAN MPO. It's our 12-fiber MPO connector. It allows one to change the gender and polarity in the field. One of the, I'll say, downsides, downside may not be the right word, but one of the downsides of the MPO connector prior to the PAN MPO coming on the scene is that it was difficult to change the polarity. On a duplex LC connectors, you sort of take them apart, swap sides, and put them back together. Can't do that with an MPO connector without the PAN MPO. And the MPO connector also has pins, and the pins on one connector slide into holes on the other connector, and those lines line up to 12 fibers. If we look how to migrate from duplex to parallel optics, here's an example of where I've got equipment in let's say a cabinet on the left-hand side, equipment on the cabinet on the right-hand side, using patch cords and cassettes and 12-fiber trunks. The 12-fiber trunks in this configuration are female, and that's because the MPO connector in the cassettes are pinned. get it all deployed, and now let's migrate to 40 gig. So replace the cassettes with MPO adapter panels. So take the trunk out of the cassette, remove the cassette, add the adapter panel, plug the trunk back in, and then I would switch from a duplex LC patch cords to MPO patch cords. And the problem without the pan MPO is that 12 fiber trunk was female because it was originally plugged into a cassette that had pins. And now you plug that in the back of the adapter panel, and now some of those patch cords, when they plug into the adapter, need to have the male pins. And that means you have patch cords with pins exposed. And there's two things that could happen when you have the exposed pins. You can break the pins off, in which case you now trashed or you destroyed the patch cord, or worse yet, you could accidentally take the MPO with pins and stick it into an optical module, which also has pins, and you can damage the end face of the connector inside the optical module. That's a costly mistake. And when I talk to customers about that, and I sort of ask the question, what do you think the odds of taking a MPO connector that has patch cord, that has pins on it, accidentally sticking it into an optical module, and basically the look on everyone's face is about 100%. With pan MPO, you can prevent the problem because I can now take the trunk and convert it from female to male, and now all my pins are protected in the adapter panel, and all my patch cords are the same, and they're all female, no exposed pins. How far can multi-mode fiber reach? So we'll start out from 10 gig all the way to 100 gig using OM3 fiber with 1.5 dB of insertion loss. 10 gig OM3 is 300 meters, and when we get all the way up to 100 gig, it's 70 meters. I don't know if it's necessarily a fundamental law of physics, but the faster you go, the shorter the distance. New fiber, well, not new, it's not new anymore, but OM4 fiber was developed to increase that distance. You can see out to 400 meters for 10 gig, and when we get to 100 gig, it's 100 meters. And one of the things that Pandu we sort of started questioning, and this was maybe 7-8 years ago, was at faster than 10 gig, what's limiting that reach? So when you look at 10 gig, you can see, this is pick OM4 out to 400 meters, and when we get to 40 gig, it's 150. What in the fiber is sort of limiting the reach? So above 10 gig, a factor or aberration is chromatic dispersion. And basically, chromatic dispersion is the same, not effect, but a prism does its thing, separating white light into many colors through chromatic dispersion. And chromatic dispersion is sort of what gives, not sort of, does, gives diamonds its brilliance. Same concept, except the light's reflected back out through the top, making a diamond shine. I mentioned the wavelength of the VCSEL is 850 nanometers, but it's not precisely 850. It's 850 plus or minus a 1 or 2 or 3 nanometers here or there. So the laser light coming out of the VCSEL isn't exactly 850. There's a tiny little spread to it. And so the impact of chromatic dispersion is we have a VCSEL. It's emitting nominally 850, but a spread of wavelengths. And those wavelengths travel down the fiber at different speeds. Just like when the white light hits the prism, the wavelengths travel at different speeds, and that's how a prism breaks up white light into colored light. And so the various wavelengths travel down the fiber at different speeds. When they get to the end of the fiber, the pulses or the modes and wavelengths are all spread out such that it spreads out the pulse. And if there's enough spreading going on, the pulses could merge together, and the receiver will have a very difficult time picking out what is a 1 and what is a 0. So at Pandu, we developed a advanced fiber, OM4 fiber, we call signature core, and basically signature core is designed to slow some of those wavelengths down such that when they pop out at the other end, they're aligned, and that keeps the pulse nice and tight. Reaches that can be achieved with signature core, 10 gig all the way out to 550 meters. And you can see at 40 gig signature core is out to 200 meters, same with BiDi, and 100 gig is 120 meters. So it's extended the range of that multimode fiber over OM4, OM3. Now, what about OM5? Basically, OM5 is a multimode fiber that has bandwidth specified at 850 nanometers and at 953 nanometers. And that is for accommodating SWDM, which is short wavelength wave division multiplexing. And basically, we would take 4 wavelengths, 850, 883, 915, and 945, combine them, put them on the fiber, and then they're pulled apart or demultiplexed at the far end. And if you're going to use those wavelengths, there has to be some bandwidth specified. So, for example, for carrying that 945 nanometers, there has to be some kind of standard specification for the bandwidth near that wavelength. So if we take a look at the 4 fiber types we have listed, there's OM3 and OM4 have a bandwidth specified 2,000 megahertz dot kilometer for OM3, 4,700 for OM4. OM5, which is the third one, has this bandwidth of 47 megahertz dot kilometer. So it's the exact same bandwidth as OM4. And our signature core, which is at the bottom of the list, has an EMB or bandwidth of 5,500 megahertz dot kilometer, exceeding all of the other fiber types. We look at the right-hand column. What's the bandwidth at 953? Well, for OM3 and OM4, it's not specified. At the time OM3 and OM4 were standardized and developed, there was no need for accommodating extra wavelengths outside of 850, so it's not specified. OM5, the specification is 2470 megahertz dot kilometer. Now you might say, look at that and say, why am I able to get away with at 953 nanometers, 2470 megahertz dot kilometer versus 4700 at 850? And that's because some of the effects that one has to contend with at 850 are lessened at 953. So, for example, I mentioned chromatic dispersion. That effect has less of an impact at that longer wavelengths. Taking a look at signature core, the megahertz dot kilometer at 953 is 2200 megahertz dot kilometer. So it's below OM5, so we can't call signature core an OM5 fiber. However, you'll see that it performs equally well. So if we look at OM5's reach for non-wave division multiplexing, OM5's reach is just the same as OM4, and that's because at 850 nanometers, the bandwidth is the same. At 850, OM5 and OM4 are functionally equivalent. If we look at SWDM4 applications, so 40 gig SWDM and 100 gig SWDM, you can see that the advantages of using an OM5 fiber versus OM4 and OM3. So out to about 440 meters using OM5 for 40 gig and 150 meters for 100 gig. And SIG core is listed, and you can see that SIG core performs as well as OM5 for 100 gig and almost as good for 40 gig, but not quite. And again, that's because signature core is not, it's an advanced fiber type, but it's not an OM5 fiber. And the last poll question, are you considering deploying OM5? So your choices are yes, possibly you're thinking about it, or no. So I would say about 3/4, maybe a little less, are not considering deploying OM5. About 2/3 and under 10% are say yes. So, should one deploy OM5? If you're not going to use SWDM, meaning if you're not going to use that module, the answer is no. It's not needed. It's not worth the extra price you'd have to pay. OM3, but in your each OM3, OM4, or signature core can do the job for you. If you're going to use SWDM, you might want to consider deploying OM5 because it's going to give you the extra reach. So if reach is an issue and you're deploying SWDM modules, then you would want to consider OM5. The third way to look at the decision is are your end user requirements. do you have to be standards compliant? And if you have to be standards compliant, then yeah, you might not deploy OM5 because SWDM modules are not an IEEE standard. And in fact, there's right now, for the foreseeable future, no work that will be done at the IEEE for SWDM modules. So even though the fiber type OM5 might be standardized, the module itself that would be connected to the fiber is not. And the reason I say does the end user require standards compliance? I don't know, 6 or 7 years ago, I was talking to a customer and was talking about some technology that was not an IEEE standard, and they told me, well, we would never adopt that. We would never deploy that. And I'm like, why? It's a good idea. I said, it's not a IEEE standard, or I shouldn't say just necessarily IEEE, but fiber channel standard. It wasn't a standardized technology, and for that shop, the edict was, thou shalt only deploy standardized stuff. So there is a segment of the population where whatever they put in their data center has to be standardized. Basically, that's the end of the webinar, and we have time for questions.
So at this point in time, you're welcome to type questions into the question or the chat box. We'll answer as many questions as possible in the time that's allowed. Tom will follow up with others that we don't have time with. If there's more specific questions and we choose not to answer it on this webinar, we will certainly follow up. As you're typing in your questions, I did want to make sure that you're aware that there are 5 handouts available that you can download. One of the handouts is a PDF of the presentation Tom just gave, in addition to some other materials that might be of interest. Also, following wrap-up of the Q&A, there will be a brief survey that we'd like you to take as well. We'll keep the webinar up so you can respond to that survey and submit that as well. So I think we could probably start. We've got a few questions already in. Again, we'll address as many as we can in the time that's allowed, and then we will follow up with any additional questions you may have. So Tom, without any further ado, why don't you
looking through the list. Why not just use a single mode because you never have to worry about bandwidth and distance again, and basically you're done with it. That is a question that's becoming, I won't say more and more popular, but is being asked more and more by end user customers. The historical reason for not using single mode or staying away from single mode was the cost, and it wasn't the cost of the fiber, it was the cost of the optical modules. Basically with single mode with a 9-micron core, the alignment of the fiber and the connector and the laser and the detector pretty tight tolerances. The laser is not a VCSEL, that's a side emitting laser, they're more expensive to manufacture. So it was basically a cost issue. However, with the rise of hyperscale data centers, so with large buying power, Facebook, Google, with their buying power, they can afford to buy single mode, not afford, but drive down the cost of single mode. And it's been, I'll say, projected for some time that single mode would approach a price parity with multi-mode. And outside of the super hyperscale data centers, that hasn't been achieved yet. So multi-mode is still less expensive than single mode. But in 4 or 5 years, maybe that won't be the case. Another question is, can you do a breakout with SWDM? I suppose you could, but it would require a special cable that has demultiplexers and multiplexers in them, and that would, I don't know how much that would cost, but I would imagine it would be a fairly expensive cable. So basically that sort of leaves SWDM for switch-to-switch links, because you can't break it out. So, well, you can do SWDM switch to server, but you're not breaking it out. You're taking that whole 40 gig or 100 gig pipe and connecting it directly to a server. So that's why, you know, in my opinion, SWDM modules, if they're going to be deployed, would be pretty much switch-to-switch links. And now that I think about it, that's where we see 40 gig BiDi being used as switch-to-switch links again, because you can't break out BiDi either. Next.
How is the integral price between OM4 and OM5?
Pardon?
How is the integral price between OM4 and OM5?
The price would be, starting at the lowest, would be OM4, then Signature Core, then OM5. I'm reluctant to give percentages or anything like that because, as they say, your mileage may vary, so check with your distributor. But in that order, OM4 would be the least expensive, then Signature Core, and then followed by OM5.
Is it a mistake to use or specify OM3 multimode fiber in lieu of OM4 fiber for equipment closet tie cables, not data center environment?
It's a mistake. I don't know if I'd call it a mistake. If you're going from the data center to a telecom closet, depending on, again, the reach, OM3 might work, but if you deploy OM3, you might be limiting yourself to 10 gig. So I wouldn't call it a mistake. We still sell an awful lot of OM3 fiber versus OM4, so OM3 is still popular, but all of the data center, all the customers I've talked to, I'd say in the past 2 or 3 years, are always asked the question, are always concerned about migrating to higher speeds. So the trend is definitely toward OM4 and Signature Core.
Next question. My understanding is there is a call for interest in process in IEEE that is expected to address SWDM applications on OM5. Can you comment?
I can't comment. No, let me back up. I could if I knew. So I don't know the answer to the question. What I'll do is talk to our Federal research people. We have several of our Federal research people are on the IEEE, sit on the standards bodies. I'll talk with them, but the last time I talked about that topic, they had told me there was no interest, or work wasn't being done.
At what distance do I have to start to worry about chromatic dispersion with multimode fiber? Will that really be an issue at less than 500 meters?
It's not so much a reach question as it is a speed question. So, for example, if you're deploying 1 gig, you don't have to worry about chromatic dispersion at all because the speed is so slow that chromatic dispersion has no impact on the stream of bits flying down the fiber. So it's a combination of speed and distance. You probably need to start worrying about you certainly need to start worrying about chromatic dispersion when you get north of 10 gigs. So that would be like 1632 gig fiber channel, 40 gig Ethernet. That's where chromatic dispersion starts to rear its ugly head.
Are there any more questions available? Is there anything that you'd like to point out, Tom, before we go forward?
No, I think that covers it.
All right. Well, we want to thank you again for joining us for this particular webinar. A brief survey will follow this. And again, don't forget the 5 downloads that are available for you. If you've got any additional questions, the chat or the question window will be open at some point in time, and we will follow up for all of those questions as well. Again, I thank you for joining Panduit for this webinar, and we hope to see you again soon.